So, we continue from where we left off in the previous class. In the previous class, we had been discussing about reflections and of course, the other parasitic elements R, L and C. We will try to see some methods of how we can mitigate the problems that arise out of these problems, these issues that we had been discussing so far. The problem of reflection, as we saw in the last class, which arose because you had two tracks and high speed digital networks. These tracks become transmission lines, and at one end of the transmission line we have the source side impedances or the source impedance RS, and on the other side of the transmission line you have the load impedance termination R naught. Now, if we saw that if the source impedance and the wave impedance are not matched, then you can have impedance at the source boundary, and if the wave impedance as seen from the output side and R naught are not matched, then you can have reflection at the output boundary. The solution to this, of course, is have RS equal to ZW, or ZW equals R naught on this side. And we have seen in the last class, instead of ZW we have used Z naught. It is common to use Z naught too to denote the characteristic impedance of the transmission line. Anyway, the wave impedance ZW should be made equal to RS on this side, ZW made equal to R naught on this side. And what is ZW equal to? Nothing but root of inductance per unit length by capacitance per unit length. So, if we need to decrease the wave impedance of the tracks, we need to increase the capacitance, that is, you need to make the lines broader, make the lines wider, so that you can reduce the wave impedance and then bring about a matching between the source side and the load side and source side and the transmission line characteristic impedance. Likewise, the matching between the load side and the track. In case that you may not be able to manage with just the track widths and spacing, you may have to include an extra component here to match the source side and the wave impedance, and probably even an extra termination to match the load side with the transmission line or the tracks. Now, one could also change the values of L and C's to bring about a change in the character of the transmission line, such that you bring about a matching of the impedances. So, on the on the tracks, apart from putting external components, one could also make printed capacitors and printed inductors. So, if you say printed capacitor, they are made by the tracks themselves. One of the simpler ones is something like this. Let us say you have a laminate, and on the laminate, on one side you have a rectangular piece of area, and on the other side, bottom side, another rectangle piece of area. And if I look from the top, if one looks from the top, it would appear something like this. The conductor portion, and you can bring it out to a pad like this. This could act as a capacitance, and to that capacitance you could connect external capacitance in parallel at these pads to achieve whatever capacitances that you would need. Now, use of printed capacitors was advantageous in some cases because they are very fast capacitors and they have the least series inductance. The equivalent series inductance of capacitors is the least, and their drift with temperature is very low compared to external capacitors that we use. This is one way of printing a capacitor on the printed wiring board itself. Another topology would be something like this. Let us have one plate of the capacitor is something like this, like a comb. It is shaped like a comb, and two combs within each other. Form quite a good capacitance. So, this would form another capacitance, and you see that the contact point is all along this length. The dielectric between this comb, the right side comb and the left side comb, is the one which is responsible for the capacitance between these two sets of conductors. So, one can print something like this, and then probably measure the capacitance and make charts out of it for a meter length, or for the length of the combs or the width of the comb, the distance between the comb teeth. The developer of the printed wiring board should start making charts that will aid him in future boards. Now, a newbie, once he makes the printed capacitor, he will not know the value of the capacitance. So, he will have to measure the capacitance by using these terminals, and these terminals should go into a bridge, an impedance bridge, and using an impedance bridge one can accurately determine the value of the capacitance and use that value for fine tuning the circuit parameters. like the impedance or impedance matching. Just like the capacitance, you could also have printed inductors. Printed inductors are also quite common. You could use few topologies. You have a pad here, and then you have a circle, another pad. So, this kind of circular loop is equivalent to one winding inductor. Okay. You could have multiple winding inductor by having a slightly modified topology. Like a spiral. So, this kind of a spiral would give you an inductor. So, you should understand that the spiral will give you multiple winding inductors, and the dielectric forms the core. Instead of spiral, one could also use a kind of a squarish spiral like this. So, this kind of spiral is also. So, this is also a possibility to get a printed inductor, many windings. I will just write it as a simple wave. Like that. That is more like it. So, these can also be used as inductor structures. So, like this you can make values of the inductors and then give these terminating pads to the impedance bridge and measure the value of the inductance. That would give you the inductance probably per unit length or per unit turn for a particular type of PCB laminate, and the developer should start making charts out of it, and then over a period of time he can have nomographs to quickly design the artwork for the printed wiring board. Now, these printed inductors and capacitors can be used at the ends of the tracks to adjust the values of the wave impedances in order to avoid the reflection problems. Okay. This is one issue. Another problem that you would see in a printed circuit board when many printed circuit boards are put together to form a bigger system is that of connectors. Connectors are sometimes, from the reliability point of view, the weakest link reliability wise. So, that is what the mill standard would say. So, there have been various connectors. If you put them on a list, you would have the wrapped joints, which is supposed to be the most reliable, reliability wise. You have the welded joints, the machine soldered joints, you have the crimped joints, you have the hand soldered joints. By hand soldered, I mean hand soldered by a professional, and then you have the multi pin edge connectors. So, you have various types of these connectors which are used for interfacing the circuits on one printed wiring board to the external world. So, if I plot on this scale unreliability, So, on this side this is very reliable, this is the reliable end, and reliability decreases or unreliability increases. Now, if you look at these connectors, the common connectors that you would encounter in almost all the PCBs, and look at what is the reliability relatively. The wrapped joint is the one which is supposed to be most reliable, and if you say that is the reference, and let us say you give a value 1, very reliable, then the edge connectors are the ones which are least reliable from the reliability point of view, and this we give a value 30. The welded joints is normally given a value 3. These are not to scale. The machine soldered joints a value 7. Crimped joints more or less like the machine soldered joints, and then you have the hand soldered joints 10. So, you will see that the various connectors have various reliability associated. So, keep that in mind while choosing the connectors for your printed wiring boards. After having chosen the connectors, electrically connectors also pose a different problem, and that is the problem related to the inductance, the mutual inductance issues. There are two major problems. Now, let us say you have a connector like this, and this is on one board. This is on one board, left side, and the right side is on another board. So, two boards are coming together with these type of connectors. So, let us say we have this is one connectors, male and female, and then you have, let us say, one more such connectors, and let us say you have a male and female of those connectors. They are connected together here, and I will take a third one. So, for a reason that I am taking these 3 pins, you should note that a connector will have many more pins, multiple pins, but I am taking 3 pins which are representative, and let us say this third pin is the ground pin, and then this is signal pin 1, this is signal pin 2. Now, you have some circuitry on this side, and then you have some loads on this side. I am just showing it as blocks. These could be digital loads and digital sources on this side, digital loads, or analog sources, analog loads, both are possible. Now, when you are talking of high speed digital circuits, okay, let us say the drivers on this side, source, you have a track which comes and connects here, and this track goes and connects to the input of the buffer stage, which is in another board. Now, from here you will have a return. The return will go to the ground pin, and this ground pin will return back here. So, normally that is how the many of the circuits will get interconnected. You have a signal going from one board to another board, and then there has to be a return path for the current. So, if you look at the current goes like this, goes through the connector, and then you have the return path, so on like this. So, if you look at this connector, this current path is a loop, and this loop, as we discussed earlier, can induce flux due to the flow of these currents, and this flux, induced flux, can link with other loops. For example, let us say you have another driver here, as I have shown. Let us say this is the other driver. Let me show it another color, and this is the receiver corresponding to that driver. Now, let me remove this and draw the track for this driver. It goes through like this, goes to this input, and then from this ground it will go into this pin, and then from this pin to this ground. So, you have the forward current and the return current. So, if I take the first circuit, the loop area is so much. This would be the loop area. Now, if you take the second, the loop area is this portion. So, you see that quite a significant portion of the loop areas are common. So, which means a current flowing through the violet loop can interact with the green loop, and the current flowing through the green loop can induce an EMF on the other loop, and this can result in what is called as crosstalk. So, therefore, we need to be very careful when we are laying out and routing the lines through the connectors. If you take the mutual inductance has two components. The crosstalk is basically a function of the mutual inductance and the important part here is d I by dt, the rate at which the current flow, the rise time of the currents. So, the rise time of the currents is a major culprit. If you are talking of very slow signals, then crosstalk is not an issue, but when you talk of fast rise time signals, then this can be pretty high, coupled with the mutual inductances of the loops. this is directly related with the loop area. So, these two together can cause crosstalk. So, how do you reduce crosstalk? Two possibilities: you can bring down this, reduce this, or you can reduce this. So, let us see. Let us say, for example, you have one connection in this fashion, and you have a driver circuit which is connected like that, and it goes on to the receiver side circuit. Of course, you have a ground, and there is a ground return path somewhere, let us say, for example. Now, the current here I, which is being driven from the source side into the load side, and then the di by dt of this is one major culprit. So, if you can reduce this di by dt, then the crosstalk can significantly be reduced. So, if you do not need such a high rise time, then one way is to put an RC in series with the circuit in this fashion. Let us say what you are going to put here is something like this. Then any rise time here is smoothened out at this point, and from this point onwards you see that the current in this portion of the loop, the di by dt is very much reduced compared to what would have been if you had not put this. This is one way, this is a brute force method of doing that one, but this is going to reduce the bandwidth of your high speed circuit. But however, keep in mind that you can do it this way, and when you are going about it, be careful, do not put the capacitor on this side, because if you put the capacitor on to this side, then you are still having a pretty high loop area. Not only that, then you are passing the high di by dt currents through the connector, and connectors can act as antenna and radiate EMI, induce electromagnetic interference, to other circuits. So, you have to ensure that you put the capacitor on the source side itself. Okay, so, that is one aspect of improving the crosstalk by reducing di by dt. There is another way, that is by interposing ground lines. Now, let us say you have this this ground connector, and the return path is coming through here like this. Now, this current, let us say for example, the current that is flowing here is split into two parts. And that two parts is like this. Now, let us say, like in the previous case, we had one more signal which is coming from another drive going to another load, then coming through the same return path. So, this is the scenario that we had. Now, let us interpose two more ground lines let us say one ground line here, probably another ground line here. Okay. So, this is also ground, this is also ground, meaning new grounds, we connect it like that. So, what happens in the return path, this line is split here and here. So, what returns through this is lesser, much lesser than if it was a single ground. So, in the grounds the current gets split and then each of the loop. So, if you look at this loop, if you take this loop, goes through like that, and the one return path is through this to this ground, this is the return path, and the other return path is through this ground, let us say, and back here. Now, what happens is that through each of these ground only half of the or part of the current flows through, and the strength of the magnetic signal is lesser, and as on the one side it is clockwise and another side anti-clockwise, you have some cancelling effect. So, this is one way of putting grounds on the outer side of the connectors, which are supposed to have crosstalk. Another way is to interpose between the two lines, signal lines, grounds. You have ground connectors in between, as many ground connectors as possible, more the better, but let us say you have many ground connectors like this, ground on this side, ground on this side. So, on both sides you have grounds like this. Now, this will increase the impedance between these two lines, and as a result the crosstalk will come down between these two lines, will come down drastically, and that will come down by a factor of 1 by n square plus 1, where n is the number of ground lines which you have interposed in between the two signal lines that matter. So, then whatever crosstalk would have been there if there were no ground lines, that divided by n square plus 1 will be the crosstalk with the ground lines. So, this way interposing ground lines at the connector points or and also in between track routings will significantly reduce crosstalks in high speed circuits. Another important point that needs to be addressed here at this point is the issue of series inductance effect. If you are having two boards and you have let us say some high speed circuit here and maybe some high speed circuit here, and you have a connector. Now, you have the line going from here to here and the return line which we expect it to go from here to here, which means that you have a path which goes like this and the return path. This forms a loop. Now, this loop can radiate and link with other loops. Now, this itself is a small area. However, the problems occur if I am having a different connector, let us say there is another connector at some other part of the board, and to which is connected this board through a cable somewhere, which may come through this or maybe from some other portion of the board. So, there can be a path through this. Let me show it in a different color. There can be a path from here, written path, which goes through here like this and returns to a ground here. Now, this is a pretty big loop area, and even a small current which flows through this undesired path can cause havoc can cause havoc to other circuits and may also not pass the electromagnetic EMI specifications. So, for such cases it may be desirable that we reduce the impedance in this path, and increase the impedance in this path. So, what we can do of course is have, let me clear up some portions. Yeah. We could have a common mode choke, so that a common mode choke where for these two lines together, forward and the return, they cancel each other. This inductance does not act as an impedance, but it forms an impedance for the line which, for the current which does not return through this, but returns through another path. So, therefore, the impedance of all other external paths will increase, and the impedance for the local path is reduced by putting this common mode choke, and thereby you try to retain most of the return path current here and reduce the loop area. So, the idea is reduce loop areas. In your track routing. Okay. So, when you route your track, see that you reduce the loop area or keep the loop area to a minimum to ensure less problems with electromagnetic interference. We next have one more issue related to analog circuits, that of capacitive coupling, which you need to be careful. So, let us say you have an op amp kind of a circuit, an analog amplifier, you have an input and the output, you have a ground here, and you are getting a source which is at a distance probably, or a high impedance source. This could be high impedance source or from a far distance like a thermocouple. Let us say you have something like this, and then you are making a diff amp, differential amplifier. So, when you have such a differential amplifier, you need to see that there are no common mode voltages. Okay, common mode voltages can be there. These common mode voltages by the differential amplifier will get differenced out, and this not reflect in the output. However, this common mode voltages can cause a problem and deteriorate the performance if the impedance seen by this line and impedance seen by this line are different, which could happen if there is a difference in coupling between this and this and this and this. For example, let us say that you have let me clear up some space here. Let us say you have a high power line. This is a high power line, and this will have a capacitive coupling to this. This is also a track. So, from this track to this track you could have one more capacitive coupling. Now, if these two capacitive couplings are different, then that could give rise to different signals here and deteriorate the performance of the output. So, it is important to see that we increase the impedance of this line, that is a positive line, and the negative line to any external line, the impedance to be as high as possible or increase it. So, one way of increasing the impedance between the line that matters and any external line is to see that we are able to split the capacitance, let us say, into two capacitances, for example. So, this is each of the capacitance now split into two capacitances in series, and therefore, we have a much higher impedance between. So, this basically is the component concept that we introduce something in between, something in between a line such that it splits the capacitance, capacitive coupling, direct capacitive coupling from any external line to the line that matters, which is the plus and the minus lines. Now, this line is called the guard line. Is called the guard line. So, if you see, for example, you have an op amp, and let me indicate them by pads, because when you do the PCB routing, it may be better visualized in this way. And let us say this op amp has a plus, minus. Imagine that the op amp is like this here, okay. And then you have lines coming out from here and gets terminated probably at connector or some other components, drivers, whatever it may be, which is basically giving you the differential source here. Now, these lines we need to guard from all external lines. So, what we shall do, we shall now erase a part of this, then give the guard in this fashion. Let us say you guard these two lines by putting a track like this all round it. So, this track, after you have put a track like this here, you need to give it a potential, and normally we will give it a potential which is the lower, that is the minus potential. So, let us connect it to this potential, or it could be connected to ground, it is called the guard ground. Now, if you, and then from here onwards you could take in these wires, and probably through the other layer you can make the connection to the inner line. So, now you see these lines are guarded from any external line which has capacitive coupling to the guard, but not direct coupling to the two lines of the differential amplifier. This will improve the performance of high precision difference amplifier to a great extent. So, you should try to use the guard concept, not only here, even in high frequency cascode stages you could use the guard concept to reduce the capacitive coupling effects on the various amplifier stages. So, these are some of the points that I thought I will put present to you. There are lots of points which you will learn as you go along in making the printed wiring boards, and you will learn more and more from experience as you start doing it. It is difficult to list down all the points exhaustively. However, this should give you a good start when you start making your PCB on a CAD package. So, before using the CAD package, brush up on these principles so that you may make the layout and routing in less number of iterations. Thank you for now.